I'm so excited to be making this video. So we're going to start off fairly simple and build up in complexity. The first thing that we need to understand is what on earth is machine learning? Okay, so if you're trying to teach a computer how to learn patterns from data without explicitly programming the computer, we say that's machine learning. To understand how machine learning works, you need to understand what you're given. So machine learning problems typically start off with an understanding of the problem itself, right? So an understanding of the problem basically means, number one, ask yourself, what data are you given? Based on the data that you're given, we can basically have what we call supervised learning and what we call unsupervised learning. Okay, so I'm going to make this fairly simple so you can understand. Okay, so supervised learning is basically saying, I give you a value of x, okay, and I tell you that the value of y is this, right? x1, y1. I give you a value of x, and I tell you what the value of y is, x2, y2. I give you a value of x, and I tell you what the value of y is, x3, y3, and I ask you to predict y4. If you've learned the relationship between x1 and y1, x2 and y2, x3 and y3, and you figured out that, okay, when x1 was this, y1 was this, when x2 was this, y2 was this, you can basically figure out y4 if I were to give you x4, okay? Because you've learned the relationship between x and y. So this is what we call supervised learning, okay? So you are supervising the computer as it learns. So you give it values of x, and it knows that the y is supposed to be this value. If it gets it wrong, it updates. If it gets it wrong, it updates. So you're supervising the computer as it does its work. And supervised learning is basically where you have x1, x2, x3, x4, and you don't have any output, right? You don't understand what's happening with this data. I just give you a lot of different data, right? Your goal is basically to understand what this is, right? Your goal is to learn patterns. Okay, so you don't necessarily have an outcome. Your goal is to learn patterns and say, maybe x1 and x2 are related, right? They belong to one thing. x3 and x4 are related. They belong to one thing. So if I were to give you x5, you can say, wait, x5 is similar to x1 and x2. So x5 belongs to this pot, belongs to this family. So unsupervised learning, you're only given values of x. You try to find the relationship between those values such that if you're given a new value of x, you can know where to put it. So based on the data that you're given, right? So machine learning problems always starts off with understanding the data that you're given. You can either have supervised learning or unsupervised learning. We also have reinforced learning. We'll do that a bit later. Okay, so in the whole part of this video, we're gonna mainly be focusing on supervised learning, right? Basically, we're trying to teach a computer how to predict values of y, how to predict output values based off of input values that we have. That's basically the whole goal. Okay, so this is quite exciting. So let's talk about it. Supervised learning. Okay, so with supervised learning, you basically have values of x, right? So values of x are values that you have, and then you have values of y. Okay, and your goal is to find the relationship. Okay, so I can give you, it's very simple. I can basically say x is the input, right? X is the input, so it can be 1, right? Y is the output, it can be 5. X is the input, it can be 2. Y is the output, it can be 5. X is the input, it can be 3. Y is the output, it can be 5. So you can realize that the relationship is weight. As values of x are increasing, y is remaining constant. I can sort of create a relationship, right? And basically learn a pattern such that if you give me x equals to 4, as a human being, I'm thinking, y must be 5 or not, right? So with a large enough data set, you can basically learn a relationship between x and y. X is the features, the inputs that will be present, and y is basically what we call the outcome or the output, basically. Okay, so another way you can visualize this, like in a more nicer manner, is basically in supervised learning. I'm going to give you a training set, right? So I'm going to give you a training set. So a training set is basically values of x and values of y, right? Input features, basically, and values of y, output features that you get. And you're going to learn what we call an algorithm, right? You're going to learn what we call an algorithm. An algorithm is a set of steps that you must take, right? An algorithm is not so complicated. So you're going to learn a certain things about your training data set, right? So you're going to learn how does X and Y actually relate, right? And if you do that, you're going to create what we call H. Okay, so this is just machine learning notation. So if you have X, which is here, which is the input, and this is Y, which is the predicted output. You're trying to learn the value of H over here. So H is called the hypothesis. So H is called the hypothesis. Okay. Why is it called the hypothesis? Well, people just named this. It's a field that people, were discovering. So they just named things what they wanted. So there's not really any logical reason to this. So H is called the hypothesis. So H is a relationship that maps X and Y. So basically, H says if X is equals to 1, Y is equals to 1. So H is responsible for finding the relationship between X and Y. So this is what we're going to be doing for the duration of this entire course. Trying to find the relationship between X and Y by creating this function called H. So you start off with a training set, then you try to learn the relationships between that data so that you can create this function H, such that first example that we're going to do is basically linear regression. So the best way to understand machine learning is through linear regression. Is I think the easiest way you can start to understand machine learning. So what is linear regression? So what is a regression problem, basically? So regression basically means you have values of Y being continuous. I'll explain what that means. And you have inputs, which are values of X. You're basically trying to learn the relationship between X and Y, which is linear, because this is linear regression, right? We can sort of predict that the relationship between X and Y is going to be linear. Okay, so what do I mean by the values of Y are continuous? If I were to give you a problem and I say, given values of X, right? Values of X can be model, can be make, can be weight, can be height, can be number of seats. So all of these are what we call values of X, right? What you're putting in. Given those values of X, Y is basically the price of a car, right? The price of a car. You can agree with me that Y, the price of a car, can be positive infinity, right? Can be $1 billion, can be $100, can be 0.111, can occupy any value that's continuous, right? It can occupy any real value that is continuous. So if I were asked to predict what the price is going to be, given these certain inputs, I can basically say that problem requires linear regression. First up, we need to do some housekeeping rules. First, we're going to talk about notation, right? The whole point of machine learning is that you need to understand your notations so that everything is set going on. X is basically called an input feature. Okay, it's a feature. So X can be any input that you put, right? If you're trying to decide whether this is a dog, for example, X can be how many ears does it have? What is the weight of that animal? So X is basically the input feature, and Y is what we call the target variable. Right? These are just, key things that you must note down if you're writing notes. So Y is the target variable, which basically implies that Y is a value that we get out, right? So it's called a target variable. And then if you want to represent a training example, right? So notation for representing a training example. So if you want to represent a training example, let's say you have 1 and 2, 3 and 4, 5 and 6, 7 and 8. So these are values of X, values of Y, values of X, values of Y, values of X, values of Y, values of X, values of Y. Okay. So we can basically say that this is what we call the first training data set. This is what we call the second training data point, the third training data point, the fourth training data point. And we can formally represent this by saying x to the power of I, so it's a superscript, y to the power of I, for I is equal to 1, 2, 3, 4, up until n. So this implies that this one is going to be this first example that we had over here at the beginning here is going to be x1. This one is going to be y1. Okay, this one's going to be x2. This one is going to be y2, x3, y3, x4, y4. So this is a way in which we can just basically explain or understand what a specific data point is. So if you see a number at the top, that just means this is the first training data example. If you see a number at the bottom, it's going to mean something else. So just keep this in mind. That's how we represent a training example. Okay. So that's good. Another thing that we need to know are basically spaces, right? So what does this mean? So x and y can be said. So if you see this e like this, it means a member of. So it can be a member of this. So it's a member of the real space. Okay. So x can be a member of the real space, meaning that it can be positive, negative, fractions, anything that you want. So x and y can be members of the real space, right? So you can see a question saying this. It means basically x and y are members of the real space, where x is the input feature and y is basically the target variable, what you'll be getting out, right? It's also possible that x can be, so x can belong, so it's going to be a member of the vector space. So if you see this R and n, it basically means that it's a real space but in vector form. So we call this a vector space. Okay, so we call this a vector space. So what this means basically is that x belongs, is a member of the vector space, right? So you can see, for example, x can be the size of a house, the number of bedrooms that the house has, the age. So you can see that this is x1, x2, and x3. So you can see that x basically is belonging to this vector space, right? It's like 3D. It's like a 3x1 vector. So if it has 3 things, it can have 10, it can have 100, right? So it basically means that there are 100 input features that we're going to use. Okay, so that's what we mean by spaces. Okay, let's now talk about linear regression. So linear regression basically should come from all these principles. Now, after the housekeeping rules are done, we should be able to get into what linear regression actually is. So for linear regression, I'm going to give you an example, right? So the example is going to be as follows. So we're going to try to predict the height of a person, right? So we're going to try to predict the height of a person, and we're going to call it y, right? So we're going to try and predict the height of a person in centimeters. So let's ask ourselves, what can belong to this specific category, right? What are the things that can belong to this specific category? So number one can be age, right? So that's going to be x1. So, okay, I forgot that little one that you're seeing here at the bottom. Okay, so that's one last housekeeping rule that I forgot. One last rule is that for multiple input features, okay, so for many input features, let's say x can be equal to age, sex, race, or something like that. For multiple input features, we basically denote them using xj transcript. For j being a member of 0, 1, 2, 3, up until n. So what this means is that you can have x1 representing the first input feature, which can be age. You can have x2, we can have x3. So it's important to realize that we have this x to the power of I representing the first training example, right? So you can have x1 to the power of 1. So what this means is that the first training example, the value of x1 for that. Okay, so for height, well, you can have age, and I'm going to call that x1, which is basically the age of a person. You can basically have the weight of the person in kgs, so I'm going to call that x2. We can basically have the parents' height. Maybe they got the genes from their parents, or some the parents are tall or something like that. So we're going to say x3, and so on and so on and so on. So you can realize that for linear regression problems, so let's do this, linear regression. So for linear regression, you're given what we call input features, right? So values of ages, right, can be 20, 30, 40, or something like that. And your given weights can be 50 kgs, 30 kgs, 100 kgs. Parents' heights can be 2 centimeters, 1 centimeter, 3 centimeters, etc. So you're given input features x1, x2, and x3. And you're asked to find the target variable or the outcome, which is y. So it's important to realize that we said when doing supervised learning, you're given x and you're trying to learn what h is, what function h is, so that you can be able to get an outcome y. Okay, so for the duration of this video, we are basically gonna do this and say h, okay, theta of x, so it's a function, right? H as a function of x is equal to, okay, so h over here is a function. Remember, if f of x is equal to 2x, it means that if I have x is equal to 1, I get an outcome which is equal to 2. F of x is equals to 2. So f of x is a relationship that maps y and x. And I can also have h of x. It's the same thing. I can also have h of x being equal to 2x. This is still a relationship that maps x and y from functions. There's a relationship that maps x and y, right? So there's nothing fancy that I've done here. I've just said h of x. Okay. So h of x, I've put that little theta here at the bottom. I'll explain later what that is. So we need to understand what x is in this context, right? So input features. Okay. If you look at this, we have x1, I. So x1 is this. So I can be 1, 2, 3, first training data set. So if you look at this, this is the first training data set. If you look at this, this is the second training data set. And if you look at this, this is the third training data set. So basically, x1i is referring to the first training data set. And then x2i refers to the second input feature, but the I corresponds to what training set you're talking about. This is x21. 1 is the superscript, x22, x23. We also have x3i all the way up until xni, depending on how many features that we have. Okay, so it's important for us to realize that these things are linear. First, you need to understand what the word linear means. Okay, so the word linear means forms a straight line. Okay, but you're going to realize that things get complicated in machine learning. So it's no longer just forms a straight line, but rather linear means if one thing increases or changes, the other, if one thing increases or changes, the other increases or changes. So that's what linear means. So in this context, if you have x1, x2, x3, xn, it implies that if x1 was to change, the outcome that you get out, h of x, which is the outcome that you were to get out, should also increase. If x2 was to change or increase, the outcome that you get should also change. But it could increase, it could decrease. You don't know, right? You don't really know, which is why for a straight line, we have the form y is equal to mx plus b, right? So if you have a line, let's say passing through the origin, its equation is going to be y is equal to mx. right? This m can be negative, right? It can be like this. It can be positive, can be like this. So negative m, positive m. So as x increases, the other could decrease, or as x decrease, the other could increase, right? The relationship can be complicated, right? So it's important to realize that in as much as they are linear, it's not a matter of one increasing, the other decreasing, right? It can be one increases, the other decreases, or it can be complicated things. So we need to add that line that you see. When you say y is equals to mx plus c, this m here is going to capture whether one increases or the other decreases. So we call this a weight, right, to x, or you can call it a parameter. I think it's better to call it a parameter, because if you call it a parameter, it's basically dictating how x changes, right? So if x is like 2 and the parameter is 2, so if you have y is equals to mx, if the parameter m is equals to 2, y is equals to 2x. If y is equals to negative 2x, that means that if as x increases, okay, y is going to increase. As x increases, y is going to decrease. So this parameter has helped me capture the relationship between x and y. And you see why I need a parameter, because like, think about this, right? As the age increases, you can expect the height to go up. So you can expect that, okay, y, edge and the height are related in this fashion, right? Edge and y. So this is height is equals to m age, right? So you can basically tell that as you increase the age, the height can increase, right? It's possible. Or you can say height is equal to m weight, right? So what this means is that if you're to increase the weight of the person, the height might go down. So you can see here that if the weight increases a lot and the height actually decreases, m has to be some sort of fraction. Having this parameter behind every input feature helps us in understanding the relationship between that input feature and the specific outcome that we want. Okay, so this should make sense why I can say theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus dot dot dot. Okay, dot 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 plus theta n x n. Okay, I don't have enough space. Okay, so what this means is basically if you increase x1, it can affect the outcome. So this is the outcome, right? It can affect the outcome, right? So x1 affects h of theta, and then x2 is going to affect the outcome by some parameter. So you can see the parameter is referred to as theta. So theta is basically the parameter, right? So it doesn't matter how many values of theta you have. Theta is basically what we call a parameter. It basically affects the values that you get out, okay? And then h theta just basically means it's a function, a relationship that relates x and the outcome given a certain parameter theta. That would be over here. But we have a problem, right? We need to introduce what you call a bias. So think about this, right? You're born as a human being, as a little baby with a certain height, right? So it's possible to have, a bias, right? Which is nothing that's affected by the features. So that's a bias, right? So you might move to a neighborhood because you're just on planet Earth, right? Everything has intrinsic value for no reason. So the bias is basically capturing all those things that are not affected by the features. So I'm just going to introduce what I call theta 0, which I call the bias, something that just present. We can't assume that when all the features are 0, that the outcome will be 0, right? Sometimes there can be a certain outcome without any of the features being described, right? You can just be born with a height and you can be like, wait, where did this height come from? You just had a height, but that height can be influenced by what you eat, and it can change with your age. So you started off with some bias when you were born as a little baby. So this can now explain why I can have h theta of x being equal to theta of 0 plus theta of 1, x of 1, plus theta of 2, x of 2, plus dot 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 dot, plus theta of n, x of n. Okay, so what this means is that this will be the bias, right? Which basically says, regardless, it can be 0, that's fine, but it basically says, if you have a value of x or not, we are going to assume that it's going to have a certain bias. Okay, so typically in questions, this has a value of x, right? X is 0, right? Which is equal to 1 for the most cases, right? So you can also write this as h theta of x, which is equal to theta 0, x of 0. We already know that for every case, x0 will be 1. Theta 1, x1 plus theta 2, x2 plus dot, 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 plus theta n, x of n. Okay, so we can do some cool mathematics here. This sign is called the summation, right? The summation, which basically says add all the things, right? So in this case, we're trying to add this plus 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 this. So you can easily realize that we can sort of break this down and combine it a little bit and say the summation from I is equal to 0 up until some value n. So theta I x of I, like this. Does this make sense? Okay, so what this means is that basically, let's expand this. What this means is summation means add. I is equals to 0 means start at theta 0, x 0 plus theta 1, x1 plus theta 2. Just replace I where this is there, plus x2 plus dot 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 theta n, xn. That's where you end. So that's what this whole compact equation basically tells you. Okay, so it's important from this now to be able to say, can I express this in vector form, right? Can I express this in vector form? You're a curious person. You're wondering, can I express this in vector form? And I would say you can. So in vector form, it's important to realize that this is equivalent to something that we are going to do here. So we can say, let theta, so just a big theta with nothing behind it, be equal to theta 0, theta 1, theta 2, theta 3, theta 4, theta 5. Okay. Okay. And then I'm going to say let x, right, without any 1 over here, like just x be equal to x0, x1, x2, x3, x4, x5. Okay, and my goal is I want to say theta times x, right? You can't do that. Remember, this is like row by column, right? This is a 1 by something matrix, maybe 1 by 10 matrix, right? And then this is a 1 by something matrix, 1 by maybe 100 or something. So you can't multiply theta and x because this is a 1 by 10 matrix and this is a 1 by 100 matrix. So you can't multiply them because these orders are not the same. So what you need to do is to first find what we call theta transpose. Okay, so I'm going to explain what that is. So it's called like this, like so. So this is called transpose. So what this basically means is that make the rows the columns, right? Flip it. Okay, so whatever was a row, make it a column. Whatever was a column, make it a row. So in this context, theta transpose will basically be equal to theta 0, theta 1, theta 2, theta 3, theta 4, and so on going down. So that's theta transpose. So it's very easy for you now to say, well, theta transpose of x. It's now possible to say theta transpose is going to be equal to theta 1, theta 2, theta 3, theta 4, okay, multiplied by x1, x2, x3, x4. And it's important to understand this. You're supposed to love math to be good in machine learning. So if you don't really like math, this course is going to be a little bit difficult. But just understand that a transpose is basically flipping rows into columns. So you take this matrix and you turn it into a column. Because it's one row, you're going to turn it into one column. Okay, so now you can do the dot product because this is basically an n times 1 matrix, and then this is a 1 by n. So like if they are the same size, if n is the same, so you can see that you can do multiplication for these guys, right? So you can basically have first row. So let's start with theta 1, first row by first column, right? So I forgot x0. Okay, so let me put x0 over there. Let me put x0, x0. So theta 0, x is 0. Row by column, row by column, row by column. So what this basically means is that you now have theta 0, x 0, plus theta 1, x1, plus theta 2, x2, plus dot dot dot, theta n, xn. Okay, so what this means is that we've just made this specific observation that h of theta of x should be equal to the summation of n when I is equal to 0 for theta I x of I, which is also equal to theta transpose. Remember, theta is just a matrix with all of the theta values that you have. Theta transpose x. X is the vector with all of the values of x that you have. So this holds true. Okay. Now you might be like, what are we doing here? What's the whole goal? We're going to get there. Okay. So our goal is to predict, right? So if I knew what theta was, right? So if I knew what theta was, right? So if I knew what theta was, let's say I could figure that out. I can find h theta of x, which is basically my prediction, right? What is the value of h theta of x? Bear in mind, h theta of x is equals to theta transpose times x. So if I were to know what theta is, the relationship, theta's relationship between all the input parameters that I used when I was training, and how it relates to my my outcome. So if I find out what the value of theta is, if I were to give you new x values, so new input variables, right? So a new age, a new parent height, things that you hadn't learned before, you should be able to get an h theta of x, which is basically what you call a predicted outcome. Okay, so the thing that we're going to introduce is basically what we call the cost function, and we'll be done. Then we'll try to basically continue in the next video. So the cost function. Okay, so it's important for us to introduce what a cost function is. This is basically a function that tells us how bad we're doing, how bad our model is. Okay, it's called a cost function because the higher it is, the higher the value, the higher the value of the cost function, the higher the costs, effectively, right? The higher the costs. So it's more expensive if we have a very high cost function. Now think about this. We're trying to predict this outcome, but it could be wrong, right? Let's say theta of x, theta transpose is wrong. And, you know, we put in new values of x. We're going to get h theta of x, which is far off. Let's say we're training this model, right? So if we're training this model and we're going to input x1 here, x1, 1, x2, 1, x3, 1, which is effectively this. Here, 20, 52. If we're to input there with the wrong values of theta, we're going to get a wrong value of h of theta x, right? And you're going to be like, huh, that's weird. Why am I getting a wrong value? Because I was supposed to have a predicted outcome, a predicted height of 100 centimeters. Why am I getting a wrong value? So we can say that's an error, right? So the error that our model makes will basically be equal to whatever it gets out. So whatever it gets out, subtract what was the actual value. So let's say x1 was actually for the first training data set. So to be more precise, we're going to call this h theta of x of I minus y of I. So let's say for the first training data set, x1, x2, x3 to the powers of all of 1, I got a value of 5. And my actual value was actually, maybe 50 centimeters. And my actual value was 120 centimeters. You're going to see that we have an error here, right? We didn't get what we wanted. So we call that an error. Okay, so you can appreciate that these values can be negative. These values can be positive. So we're going to square those. We're going to square this. Okay, and then we're going to have y of I. We're going to square that. So basically, we're going to square this. And because we want to eliminate negative, right? We just want to keep it positive. You can now sum it all for all the different values that you have. So you have x1, x2, x3, because you can have error 1, which is h theta of x1 minus y1. For the first training data set, you can have error 2, which is basically h theta of x2 minus y2, all of that squared. You can have error 3, error 4, error 5, and so on. So you can basically say that the sum of all the errors will basically be equal to the summation of n from I is equals to 0 for all of your errors h theta of x to the power of I minus y to the power of I squared. Okay. So this is what you call the cost function, right? And we're going to do something here. So j of theta is what we call the cost function. It has a specific format. So this is what we call the cost function, j of theta. And j of theta is going to be, so we usually put a half behind this just to be fancy, to be honest. So we put a half, and we have this summation of n, I is equals to 0, and we have h theta x transpose minus y I squared. Okay, so this half is going to be useful later, right? So remember, our goal is to minimize. So the goal, so this half, don't worry about where it came from. I just plugged it. It's a number. It doesn't change the concept. I can do whatever I want. This is machine learning, which is quite fun. Okay, so the goal is basically we want to minimize j of theta, which is what we call the cost function. The goal is to minimize j of theta. So choose values of theta to minimize j of theta. In the next video, we're going to explain how to do this. So this is basically how you can select correct values of theta, because we're trying to minimize the error that we get out by trying to basically minimize this function j of theta. So basically that's the basic introduction to machine learning and using linear regression as an example. So in the next video, we're going to talk about how to actually learn and find values of theta. But a brief summary, we started off by understanding what machine learning is, right? We want to teach a computer how to learn to predict patterns from data without being explicitly programmed. We talked about how the whole point of machine learning is to find what data you're given, right? Does this data have an output? If it does, we can do supervised learning. Does this data not have an output? You're just given random features and you're trying to learn the pattern between them. We can say that's unsupervised learning. If it's supervised learning, you have values of x and values of y, and your goal is to find a relationship between those two things. Find a function that relates x and y. And effectively, with every machine learning problem, you start by being given a training data set, and then you're supposed to learn a specific algorithm that will help you to find the value of h. So that's what we're going to be doing. But after you have the value of h, which is called the hypothesis, it's basically going to be able to relate x and y, right? And we say the first problem that you might see in life is a supervised learning problem, which is known as linear regression, right? The values of y are continuous. They exist from negative infinity to positive infinity, negative, positive fractions, all you want. And you have certain input values of x, and you want to learn the relationship between x and y, which is linear. Linear means if one thing changes, the other changes as a result. And we said that the notation that you need is to understand that x is an input feature, y is a target variable. We also explained what a training example is. This is what we call a training data set, where you have x to the power of I being the first training example, x to the power of 2, the second training example. All of these are input features, by the way, and y to the power of I represents the output that we get out. And we say that x and y can be part of certain spaces. So x and y can be part of the real space, or can be part of the vector space. Vector space implying it can be 3 by 1, or it can be 4 by 1, it can be 100 features, like x1, x2, up to x100. So we need to put this number over here to indicate what space we're dealing with in the vector space. We also have discrete space, continuous space. We don't really care about that. And we say that if we have multiple input features, remember that the number at the bottom, x1, x2, x3, basically refers to what specific feature you're referring to. So the number at the bottom is what feature. And the number at the top is what training set. And this number is fixed for multiple features. So you can have x21, x31. Okay. And then I give you an easy example and I say you want to predict the height of a person, and I give you multiple input features: age, weight, parameter, parent's height, and you want to predict the height. That's a simple linear regression problem you might solve teaching computer how to do this. So you have X, you want to learn the relationship Y. Okay, then I said we can basically assume that this relationship h of theta x is linear, meaning that if one thing changes, the other changes. So we can introduce parameters, coefficients behind these input features, right? So these coefficients, theta 1, theta 2, theta 3, basically affects how each input thing affects the outcome. Okay, then I said we also need to introduce a bias, because it's also possible for nothing to be affected by the features, right? You're born with a certain height that wasn't really affected by any feature externally. So we say that's a bias. So for most things, there's going to be a bias which doesn't have any feature related to it. And we said it can be attached with x0. So that's basically, which is equals to 1. That's how you represent an entire learning rule for a linear regression problem. And we said you can sum all this up as theta I, x to the power of I. In vector form, theta can be expressed in this specific form, but its transpose is basically flipping the rows to be a column, and you basically have this transpose. X can be expressed in this form, and the product of this transpose row by column, gives you back that same rule. So you can basically say that your learning function or your hypothesis, so you can basically say that your hypothesis for a linear regression problem is basically theta transpose multiplied by x. So if you know what theta is, roughly you can find what values of theta of x are. So if you have values of x, let's say x1 for the first training data set, you try to find this and you get it wrong, you already know what the answer is. So your machine tries to learn and it gets it wrong. It can basically calculate the difference. We square that difference, we find the summation of that, we introduce a half for some reason. We basically create what we call a cost function, which basically tracks how many mistakes we're making. And our goal is to minimize that cost function so that we can have the right values of theta. Because if we have the right values of theta, and if we plug them here, we can basically predict new values of x when we don't have any values of y given out. Thank you.